This video is about limit. Here is the informal definition for limit. If f of x can be made as close as we like to some real number a by making x sufficiently close to but not equal to a, then we see that fx has a limit of a. As x approaches a, we write this. In this case, fx is said to converge to a as x approaches a. If fx and g of x are functions such that limit as x approaches a of fx and limit as x approaches a g of x exists, c is a constant. We have the following formula. These formula are easy to remember. If you have constant c, you can take c out, and this plus or minus, that you can separate this limit. Multiplication, we still can separate the limit. Division, then separate the limit also. In what situation a limit exists? The limit of a function fx exists if and only if the one-sided limits of the function are equal to each other. In other words, there is limit as x approaches c of fx equals to L. If and only if limit x approaches c from right side fx equals limit x approaches c from left side fx equals to L. Here are some methods for evaluating limits. First of all, just try direct substitution. Say if it's defined or undefined. If it's defined, then just use direct substitution. When you do the direct substitution, they give you undefined answer. For example, you have 0 as a denominator. Then you can try factoring or rationalizing. That means conjugate. Or if you have a complex fraction, then you can simplify complex fraction. Now let's go to guided practice 1. Evaluate the following limits. For a, since this is a given polynomial function, domain is all real numbers. Therefore, you just need to plug in. You will get the 5, 2 squared minus 3 times 2 plus 2 equals 16. For b, when you plug in this 2, you still get the constant number 7. For c, when you plug in 1, it's defined. Therefore, we do 1 squared minus 3 times 1 over 1. Negative 2 over 1 equals negative 2. Let's go to D. When we plug in this 8 into this function, you will get the denominator is 0. So it's undefined when you do direct substitution. Therefore, you need to do factoring. Quadratic function, we do ninja x. So we have 16 negative 17 over 2 over 2. 16, I can do 1/16 adding is 17, but I'm looking for negative 17. So we both put the negative sign. That is negative 1 and negative 16. Reduce negative 8 over 1. Then variable is z. Then we do bottom up. You will get the limit as z approaches 8 of z minus 8 and 2z minus 1 over 8 minus z. We know that a minus b over b minus a. When you reduce, you get negative 1. Therefore, z minus 8 and 8 minus z, we reduce, we get negative 1. So, we will get the limit as z approaches 8, negative 2z minus 1. This time, you can just plug in. So we have negative 2 times 8 minus 1. That's 15. We have negative sign, negative 15. Now let's go to E. When we plug in 0, we still get the denominator is 0. So it's undefined. If it's undefined, just check. You cannot factor. We do have these expressions. So we can do rationalizing. Or we call this a conjugate multiply. We can do the limit as x approaches 0. 3 minus square root x plus 9. Then times is a conjugate. 3 plus square root x plus 9. For the conjugate multiply, we know that a plus b times a minus b. That is a squared minus b squared. Therefore, for this one, we will get the 3 squared minus square root x plus 9 squared. That is 9 minus parentheses x plus 9. Then do distributive property for this negative sign. 9 minus x minus 9, you will get negative x. So we put the negative x top, that is x 3 plus square root x plus 9. Then reduce. You will get limit as x approaches 0, negative sign 3 plus square root x plus 9. This time we just plug in negative 3 plus square root 0 plus 9. You will get negative 6. Now let's go to F. We know this is a complex fraction. When we do direct substitution, you will get the denominator is 0. Therefore, we simplify this complex fraction. Check denominator. I have x, here's 4. So LCD equals to 4x, which means the denominator I multiply by 4x. Numerator, I need to multiply by 4x. So we will get the limit as x approaches negative 4. X plus 4 times 4x. Look at the top. 4x do the distributive property. You have 4x over x plus 4x over 4. Then reduce. You will get the limit as x approaches negative 4. X plus 4, 4x. 4 plus x. Then I can reduce now. You will get the limit as x approaches negative 4 of 1 over 4x. Now we can do the direct substitution. 1 over 4 times negative 4, that is negative 1 over 16. Let's go to guided practice 2. Below is the graph of fx. For each of the given points, determine the value of f of a and limit as x approaches a f x. If any of the questions don't exist clearly, explain why. For a equals negative 3. So check f of negative 3. We do have this closed circle. That is 4. So we get 4. For the limit, when you check whether limit exists or not, you have to make sure the left side and also the right side. So limit as x approaches negative 3 from left side. You can check, this is the left side graph, so we approach to this negative 3, you will get 4. Then for the limit as x approaches negative 3 from right side fx. On the right side of this negative 3, the graph is here, so we approach this negative 3, you will get the value negative 2. Since they are not equal to each other, therefore, for limit as x approaches 3 fx doesn't exist, not available. Now, for b, a equals negative 1. We will work out f of negative 1. Find that negative 1 is here. This is a closed circle. Therefore, f of negative 1 equals negative 3. For the limit, as x approaches negative 1 from left side, this is your graph, approaches negative 1, you will get 1. For the limit, as x approaches negative 1 from right side, it still get 1. Since these two equal to each other, therefore, limit as x approaches negative 1, fx equals to 1. Now let's go to C. A equals 2. F of 2 equals, we don't have closed circle, we only have an open circle. Therefore, it's not available. It's undefined at x equals 2. Limit as x approaches 2 from left side, fx equals. This is a left side, so approaches 2, you will get 1. Limit as x approaches 2 from right side, fx equals. Right side the graph approaches 2, still get the 1. Since one-sided limits are equal to each other. Therefore, we know limit as x approaches 2 fx equals to 1. Now let's go to D. A equals to 4. F of 4 is here. That is 5. Limit as x approaches 4 from left side fx. Check the graph from left side approaching 4. You will get 5. Limit as x approaches 4 from right side. From right side of this graph approaching this 4, you still get the 5. When the function value and the limit's value are equal to each other, we say the function is continuous at x equals to 4. Here's the official continuity. A function is continuous at C when the following 3 conditions are met. F of C is defined. Limit as x approaches C fx exists, and limit equals to this function value. Since these 2 limits are equal to each other, we can draw a conclusion. Limit as x approaches 4 of fx equals to 5. Guided practice 3. Given hd, this is a piecewise function. Evaluate the following limits if they exist. For limit as z approaches 7, h of z. When z approaches 7, you have to use this function. We can do direct substitution because it's defined. So 1 minus 9 times 7, negative 62. Let's go to B. Limit as x approaches negative 4 h of z. Since negative 4 is the boundary point, so you have to check limit as z approaches negative 4 from left side, h of z. From left side means when z less than or equal to negative 4. Basically, we can just plug in 6 times negative 4 equals negative 24. Limit as z approaches negative 4 from right side. You have to use the function as z greater than negative 4. So we plug in 1 minus 9 times negative 4 equals 37. Since these one-sided limits are not equal to each other, therefore, this limit not available. Now let's go to limits at infinity. We write this means when x gets as large as we like and positive. This one to mean when x gets as large as we like and negative. We read x tends to positive infinity or plus infinity. We read this as x tends to minus infinity or negative infinity. This is the formula. You have to remember limit as x tends to positive infinity 1 over x equals to 0. Limit at infinity normally used in rational functions for asymptote line. We have 2 asymptote line for this function. As x tends to fall from the left, fx tends to negative infinity. As x tends to fall from the right, fx tends to positive infinity. As x tends to negative infinity, f of x tends to 2 from below. As x tends to infinity, fx tends to 2 from the top. Since fx converges to a finite value as x tends to negative infinity, we write limit as x approaches negative infinity fx equals 2. Since fx converges to a finite value as x approaches positive infinity, we write limit as x approaches infinity fx equals 2. Guided practice 4. For each of the following functions, discuss the behavior near the asymptotes and hence deduce their equations. First of all, we need to figure out the following properties for this rational function. We use a diagram to figure out the root, vertical asymptote line, horizontal asymptote line, and a y-intercept. Since this is a linear over linear rational functions, we only need these 4 properties. That's enough to sketch the graph. We do root first. We make a top equal 0. That's x equal to 0. So we have 0, 0. That's the root. For vertical asymptote line, we make a denominator equal to 0. So 1 minus x equal to 0. X equals to 1. We do this dotted line. For horizontal asymptote line, you got to use this limit. Basically, for horizontal asymptote line, that means the leading degree. You have x, here's a negative x. We do divide x over negative x. You will get negative 1. So y equals negative 1 will be horizontal asymptote line. For y-intercept, that is f of 0. We plug in, you will get 0. So 0, 0. Now we can sketch the graph now. Since for linear over linear pattern, we only have 2 types of graph. One is a vertical asymptote line and a horizontal asymptote line, either like this or like this. So basically, we need to draw the vertical and horizontal asymptote line. X equals to 1. We will draw like this. Y equals negative 1. It's like this. And for the roots, that's a 0, 0. It's here. You can predict the graph like this. Now we can discuss the behavior near the asymptotes. x tends to 1 from left side, y go to positive infinity, while as x tends to 1 from right side, y goes to negative infinity. And x tends to negative infinity, y tends to negative 1 from top. X tends to positive infinity, y tends to negative 1 from the bottom. In other words, for these two limits, both equals to negative 1. Now let's go to this b. For the root, you will make a top equal to 0. 1 minus 2x equal to 0. X equals 1/2. So we can write down 1/2 0. For the vertical asymptote line, we make a denominator equal to 0. So x equals negative 2 over 3. This is a vertical asymptote line. For horizontal asymptote line, y equals, check the leading degree. You have negative 2x over 3x. That is negative 2 over 3. For y-intercept, you have f of 0. 1 minus 2 times 0, 3 times 0, plus 2. So you will get 1 over 2. 0, 1 over 2. We'll show vertical asymptote line, that is negative 2 over 3. Like this. And horizontal asymptote line, that's negative 2 over 3. That's y equals that. And root, it will be 1/2 0 here. For the y-intercept, that's 0, 1/2. Now we can predict the graph like this. Now discuss the behavior near the asymptotes. X tends to negative 2 over 3 from left side. Y tends to negative infinity. X tends to negative 2 over 3 from right side. Y tends to positive infinity. X tends to negative infinity. Y tends to negative 2 over 3 from below. X tends to positive infinity. Y tends to negative 2 over 3 from top. And we can draw the conclusion that limit as x approaches negative infinity fx equals negative 2 over 3. Limit as x tends to positive infinity fx equals negative 2 over 3.